right, Chemistry 3111. Let's start chapter 19, which is the chapter on aldehydes and ketones. I know that you all know what an aldehyde is and what a ketone is by now. You certainly don't need my help with an aldehyde, which is where we have a carbonyl with one R group and one hydrogen, and then a ketone, which is a carbonyl that has two R groups, one on either side, like that. All right, you guys know that really, really well. And I'm going to come back to this slide in just a second, but I want to go all the way to the end and show you, where is it? Somewhere around, oh boy, Mr. Dion can't see here. All the different reactions that you have to learn in this chapter. So it's somewhere down here. Okay, it's the last slide. So you can see that in this chapter, we cover a lot of different reactions. Now, before you get intimidated by this slide, I can actually show you that you can organize this into a few main parts, okay? We're going to talk about what's called a hydrate or an acetal, and that would kind of cover this portion right here. Then I want to get through most of that with you today. Then on Wednesday, I'd like to start this part on nitrogen. So we talk about what's called a nitrogen nucleophile. And then there's a smattering of some other reactions here, like reductions and Grignards and halo cyanohydrins, rather. And then towards the end, we get into this reaction here, which is one of the most important reactions in all of organic chemistry. It's called the Wittig reaction. And then we cover this one here. This is called the Baeyer-Villiger reaction. And I'll go over that one with you too. And then, of course, there's the Raney nickel reduction reaction here. So like I said, you can once you get the hang of a couple of these, it will take you quite a ways as long as you understand how to form an acetal, how to form an imine or an enamine. And then finally, some of these other, like for example, this reaction is one you covered already, right? We covered that in the alcohols chapter, right? So, like I said, quite a bit of content in this chapter. But again, my job as your instructor is to lay it out, not in a simple way because there's nothing simple, but in the most straightforward way I can. So again, what do an aldehyde and a ketone have in common, right? Why are they in the same chapter? It's because they both possess a carbonyl group, okay? And I understand that carbonyls are also found in esters, carboxylic acids, amides, etc. However, aldehydes and ketones share a lot of similar reactivity and reactions, as you saw on that last slide. And they're important in biology and industry. For example, the simplest possible aldehyde that you can have is formaldehyde. And you guys probably know that that's used as a preservative. Formaldehyde itself is actually a gas, but you bubble it through water to make formalin, which is used as a preservative. The next one is on the bottom right-hand side is the simplest possible ketone, and that's acetone. And acetone is nail polish remover. So this is nail polish remover. But acetone has many uses. You know, you probably used it in the lab to clean glassware sometimes. It's used as a reagent. It's used as a solvent. It's used as a paint thinner. Acetone has a wide variety of uses, okay? So where would you find aldehydes and ketones in your everyday life? Everywhere. They're pretty ubiquitous in terms of naturally occurring compounds. So if you like vanilla flavor, I do. I like vanilla ice cream or cookies with vanilla in them. And so vanillin, you can see, has an aldehyde functional group in it. Cinnamaldehyde, this is trans-cinnamaldehyde, which gives cinnamon flavor, that has an aldehyde in it. If you like the flavor of spearmint, like spearmint gum, you can see that carbone has a ketone in it. And benzaldehyde is responsible for almond flavor. You see the male and female sex hormones here. So testosterone and progesterone, they both have a ketone in them down here. And you see that progesterone has two ketones in it. So aldehydes and ketones, very abundant in nature. In fact, if you look up, the top 200 marketed drugs by sales that I showed you earlier on, you can find all kinds of compounds that possess aldehydes and ketones. So what does that mean? It means somebody like you or me who's studying more organic chemistry, or somebody who wants to develop medicines to extend and enhance human lives, has to understand the chemistry of aldehydes and ketones, the same way they had to understand electrophilic aromatic substitution and SNAR and elimination, addition, all that kind of stuff in chapter 18. So let's start out with some nomenclature. And there's 4 discrete steps to naming an aldehyde or a ketone. It's the same procedure for naming an alkane, alkene, alcohol, etc. Number 1, you identify the parent chain. So you find the longest chain that possesses the functional group. You identify the name of the side substituent. So is it an isopropyl, a chloro, a fluoro, an ethyl, what have you? You give a locant to the substituents. Is it 3-ethyl, 2-chloro, etc.? And then you put them all together in alphabetical order, right? So you list all the substituents in alphabetical order. So let's take a look at some examples. I think it's the best way to master nomenclature. And we're going to start with aldehydes. And the way that you name the parent chain for an aldehyde is you drop the E suffix from an alkane and you replace it with al. All right, so if you have butane, then if you have a 4-carbon aldehyde, 1, 2, 3, 4, it becomes butanal, right? Let's imagine you had 1, 2, 3, 4, 5. That would be pentane. Okay, you would drop this and 1, 2, 3, 4, 5. You would call this pentanal, right? Pentanal, hexanal, heptanal, octanal, so on and so forth. So the parent chain, just like an alcohol, has to include the functional group, or just like an alkene. So it has to include the carbonyl carbon. And the thing is, what's interesting about aldehydes is with an aldehyde, you don't have to include a locant for the functional group because the aldehyde always has a hydrogen on one side. So you don't have to say, 1-hexanal. That's redundant. Of course, the aldehyde is at the end of the longest chain. Okay, it's not the same for ketones, but for aldehydes, you don't have to include a locant for the carbonyl itself. Now, I'm never going to ask you to name compounds like this one here with 3 functional groups, so I'm not even going to worry about that. But anyhow, the bottom line is if you ever see a compound that has more than 1 functional group, and you can see here we have an aldehyde, we have an alcohol, and we have an alkene. If you're ever wondering, which one of these takes precedence, well, there actually is an order of precedence of compounds in organic chemistry. And if you have a carbonyl, any compound with a carbonyl will always take precedence over an alcohol, and an alkene. Okay, so if you look at this compound overall, you say, how would you describe this compound? Would you call it an aldehyde, an alcohol, or an alkene? You would call it an aldehyde. Now, again, I'll never ask you to name a compound like this, but I can show you just for instructional purposes. This compound is called 5-hydroxy. So the hydroxyl group is called a hydroxy. The hydroxyl is given the prefix hydroxy. And then we have a 5,6-dimethyl. So 5,6-dimethyl. Then to stick the alkene in there, you would say 6-heptene or hepten-al. Okay, that's how you would name this compound. But again, I will not ask you to name a compound that complicated. Okay, the class is difficult enough. So I hear ye, okay? I will not ask you to name a compound with an alcohol, an alkene, and an aldehyde in it, okay? It won't happen. Now, with a ketone, what you're going to do is you're going to replace the E suffix from the alkane with -one, O-N-E. And it says here the parent chain has to contain the carbonyl. However, in this case, unlike an aldehyde, you do have to provide a locant or a number for the ketone. And so you want to find that longest carbon chain, but just ignore everything else. The rule is you want to give the carbonyl carbon the lowest possible number. Okay, forget about the rest. Just give the carbonyl carbon the lowest number, and the rest just put it the way it is. Okay. So I told you that there's a couple of ways you can do this when we looked at alcohols. So we could say 3-heptanone, or we can say hepten-3-one if you really want to be cheeky. Either one is perfectly acceptable. They're both accepted by IUPAC. There's nothing wrong with either of them, okay? Now, let's say you have a chiral center. Right here we have a chiral center in this compound, right? The chlorine takes highest priority. The carbonyl is 2. This is 3. And of course, we have a hydrogen, which is coming out towards us, which is going to be number 4. So we're going to go from 1 to 2 to 3, which would be S, because we're going in the counterclockwise direction. But remember, the proton is coming out towards us. So we reverse that, and that means that this stereocenter is R, so this would be R2-chloro-3-phenyl propanal. The next one, what if you have your aldehyde group attached to a ring? This is one you just kind of have to memorize it. It's called a carbaldehyde. Is that a weird name or what? Okay, we call it where's my pen? We call it a carbaldehyde. So you would just call this cyclohexane carbaldehyde, okay? Again, it's just one of those one-off kind of things that everybody has to learn what a carbaldehyde is. Now, in terms of small aldehydes with common names, I put the table here. Okay, so IUPAC recognizes common names for these aldehydes. Like if you have one carbon, right, instead of methane, it would be methanal, right? But it does have a common name, which is formaldehyde, and you have to know that common name. If you have two carbons, then it would be called ethanal, and the common name for that is acetaldehyde. And then we have benzaldehyde. But if you remember, you were asked to memorize this way back in chapter 17. So something that I learned when I first started teaching this class at UCCS years ago is that I think it's kind of taken for granted that you know the common names for actually the first 5 aldehydes. So let me show you what I mean. I actually took this table out of a different textbook. This actually comes out of the nursing textbook, okay? So they expect you to know when you have 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons, or at least I think it's useful for you to know this, okay? So if you have 1 carbon, it's methanal. The common name is formaldehyde. If you have 2 carbons, it's ethanal, would be the IUPAC name. The common is acetaldehyde. If you have 3 carbons, this is where it gets kind of weird, is with these two, okay? It's propanal, but the common name is propionaldehyde. And then for butanal, the common name is butyraldehyde, okay? So these are propion and butyr with a Y, okay? They're kind of weird. And then for pentanal, it's valeraldehyde, but my students always say, well, it's V, like a Roman numeral 5, so 5 carbons valeraldehyde. Maybe it's easy to remember that. But I've done enough looking around the internet and at MCAT materials and that I think it's a good idea to know these. Good idea to know these names, to know these. And what I mean by these are really just these 3 here. So propionaldehyde, butyraldehyde, and valeraldehyde. All right, so let's see if we can come up with some names for what do we see here. We got an aldehyde and 2 key. Oh boy, we got some stereocenters in here too. Let's tackle these. And the first one, if we find the longest carbon chain, it's got, look, 1, 2, 3, 4, 5, 6. So this is some kind of heptanal, or sorry, a hexanal rather. So this is a hexanal. Okay, we've got that. Then we've got 2,2-dimethyl. So I'll just scribble down what we know, 2,2-dimethyl. And then we have a 5,5-dibromo. So 5,5-dibromo. Remember that we ignore the di prefix. We alphabetize according to the letter M here and the letter B here. So the dibromo would come first. And so this compound's name would be 5,5-dibromo 2,2-dimethyl hexanal. All right, give me a thumbs up if you're with me on that one. Like, that one's not too bad. All right, cool. Let's try the next one. The next one's a ketone. It involves a couple of stereocenters. So 1, 3, 5, 6. So it's some kind of 2-hexanone. So this is a 2-hexanone. There we go. Let's figure out the 2 stereocenters. So we'll start with stereocenter at carbon number 3. So there's 2 stereocenters, right? There's 3 something, 4 something, okay? And then we've got 1, 2, 3, 3, 4, 5 trimethylhexanone. So I'll scribble that in here. 3, 4, 5 trimethyl hexanone, like that. Okay, let's figure out the stereocenter at carbon number 3. You guys have probably done it already. Talking. Okay, so the proton is out in front. So we've got number 1, number 2, number 3. So we go like this, which is counterclockwise. That would be S. We flip it, so it's R. So it's 3R. And then did anybody figure out the next one? Did anybody figure out the one next to it? So if I put the proton out here. No? Okay. No, Erica says it's S. So let's see here. So we have 4, 3, and then this would be 1, and this would be 2. So we go 1, 2, 3, which would be R. We flip it. Thanks, Erica. 100% correct. So 3R, 4S, 3,4,5 trimethylhexanone. And the last one, did anybody come up for a name for the last one while I've been talking? I'm sure you guys did it faster than me. 1, 2, 3, 4, 5. So it would be what? 2,2,5,5 tetramethyl cyclopentanone. So 2,2,5,5 tetramethyl cyclopentanone. There we go. Not too bad. All right. Oh, I got some other ones in here. Oh, I put in a couple of diketones. So check this out. If you have to name a diketone, I put this on because I've seen this in DAT materials. And MCAT, I don't know if they're in there or not. I've never seen them, but I know I've seen it in the DAT. So it's probably in the MCAT too. So maybe I should just erase that. But for a diketone or a triketone, it's pretty straightforward. You just, instead of one, you just put dione. If there's 3, you put trione, okay? So here, you just find the positions of the carbonyl. So 2, 3, so you'd call it 2,3-butane dione. So if this is cyclohexane, you'd say 1, 2, 3, 4, 5, 6. So you'd call this 2,4-cyclohexane dione. Is how you, or sorry, 1,4-cyclohexane dione. And then for the last one, the one on the bottom, you'd say 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 2,5,8. So 2,5,8 nonane trione is how you would name that. Nonane trione. Okay, trione. So 1 is, so like the bottom line is this: if you have 1, come on. Okay, if you have 1 carbonyl, it's going to end in -one. If it's 2, it's dione. If it's 3, it's trione. If it's 4, it's tetrone, etc., etc. Tetrone. I can't imagine seeing anything with more than 4 carbonyls in it. That's crazy. All right. So I have some good news for the next couple of minutes. We're going to actually look at a bunch of reactions that you already studied in gory detail this semester. Okay. So now we're going to do some review, because if you think about in the alcohols chapter, we did a whole section on oxidation. Right, we learned Swern, Desmartin, Jones, what else? PCC. And so we learned a whole bunch of ways to make aldehydes and ketones. And so let's review that because it's pertinent for this chapter. So a summary of aldehyde preparation. So if you have a primary alcohol, if you use a mild oxidizing agent, when it says mild oxidizing agent, all it means in this class is not chromic acid. That's all it means. Don't use chromic acid. All the other oxidizers, whether it's PCC, Desmartin peroxidinane, remember this one here, this is the Swern. All of those are just going to oxidize your primary alcohol to an aldehyde. Remember, if you take the aldehyde and you treat that with chromic acid, right, that's going to oxidize it further to the carboxylic acid. But this is for another chapter, right? The topic of this chapter is not carboxylic acids. So let's not worry about those. Now, what about ozonolysis of an alkene? Right, we talked about ozonolysis of alkenes in detail in Organic Chemistry 1. And so let's say you have an alkene like this one here, you treat it with ozone and DMS, right? You end up breaking this bond and you end up with a pair of aldehydes as is shown here. Also, what if you had, actually, I think the part about the ketones is coming up, so I'll just leave it like that. Next one, what about making an aldehyde from an alkyne? Okay, this is a chapter 9 reaction that we haven't really thought about much since the very beginning of the class. Okay, so if you have to review this one, hydroboration oxidation on a terminal alkyne, remember that this reaction produces an enol rather, and the enol undergoes tautomerization, right, to give you the terminal alkyne, or sorry, the terminal aldehyde, sorry, the aldehyde, like that. So remember when it says R2BH, this step here, this could also be 9-BBN. 9-BBN is totally fine for that. What else? Secondary alcohols. If we oxidize those, you can use the strong oxidizing agent, or you can use a mild oxidizing agent too. So to do this reaction, you could also use PCC, SWERN, etc. When I say etc., I mean the Des-Martin reaction. Okay, they all work. All right. And then this is the one I was going to start talking about and stopped myself, is if you have a tetrasubstituted alkene, that's going to give you a pair of ketones when you do the ozonolysis. Also, one that's not in here is what if you had a tri-substituted alkene like this, right? In that case, if you treated it with ozone followed by DMS, in that case, you would end up with a ketone and an aldehyde. So that's kind of a cool reaction, right? You get an aldehyde and you get a ketone like that. What else? Again, this is one that we haven't really talked about since chapter 11. This is the acid catalyzed hydration of a terminal alkyne. So that's the Markovnikov addition. So this one is going to give you this enol. So you'd have this enol, and that enol is going to undergo tautomerization to give you the methyl ketone. So that's a way to make a ketone. Again, these are all reactions that we would have seen previously in the class. Friedel-Crafts acylation. Hey, we just covered that. We talked about that today, right? So that's a chapter 18 reaction. And so it says here, if you have an aromatic ring that is not too strongly deactivated, remember, Friedel-Crafts doesn't work if you have a moderate or a strong deactivator. Then you can install a ketone like that. So you can make an aryl ketone. So that's a kind of a cool reaction. And so now that we've kind of got those reactions fresh in our brain, which I know you all did anyway without my help, let's just see if we can try a couple of these just to kind of flesh out some ideas, and then we'll try something new. Okay, so let's say we had this secondary alcohol in 19.5A, and we want to make cyclohexanone. I mean, what are the possibilities? It's literally everything that we've ever learned. Okay, so for A, you could use, I'll put here, you could use PCC and dichloromethane. You don't even have to put a solvent, that's totally fine. You could use the Des-Martin periodinane, so DMP, which is also done in dichloromethane. You could do a SWERN reaction. In the step 1, you use oxalyl chloride and DMSO. So I'll put here DMSO and oxalyl chloride. And then in the second step, you use triethylamine. I would even say, of course, you can use the Jones reagent. So I would say you could use sodium dichromate, sulfuric acid, and water. That will work, but that's doing a strong oxidation in acid. You can also do it in base if you use potassium permanganate. So step 1 is going to be potassium permanganate, water, and heat. And then in the second step, use H3O plus. So literally, this, and this, all of these methods will work to oxidize a secondary alcohol to a ketone. Now for the next one, we can avoid the sodium dichromate and the potassium permanganate because we want to stop at the aldehyde, right? So in that case, all we're going to have at our disposal is going to be PCC and DMP. So we'll copy these. put them down here. And then, of course, we can also use the swern. So we'll bring that one down here as well, too. Swern, nothing wrong with that. So all three of those are possible, but not chromic acid. That won't work for this one. All right, there we go. The next one, we want to do the conversion of a terminal alkyne to a methyl ketone. So that's going to be the acid catalyzed addition of water to a triple bond. And so if you don't remember, kind of the key step there is that you've got to have sulfuric acid and water, but you also need mercuric sulfate. So sulfuric acid and water, but you need HgSO4, mercuric sulfate, right? Because it's too unreactive without the mercuric sulfate. And the last one, we're making the aldehyde off of a terminal alkyne. So that's the reaction with 9-BBN. And so our first step is going to be the 9-borobicyclic nonane, followed by hydrogen peroxide and sodium hydroxide. And again, for this part, you can put R2, BH, or what was the other one they had? Was dicyamylboron, dicyamylborane. Any of those are fine for the hindered borane. All right. There you go. Everybody with me so far? We finished the first three sections. So the first two are new. We did a little introduction about aldehydes and ketones. Then we tried some nomenclature. Now we did a review of the reactions that we already knew that involved the formation of aldehydes and ketones. So now that we've covered that, we're going to get into nucleophilic addition reactions to a carbonyl group. Okay, so this is going to be a lot of new chemistry. And I'd like to try to get up to the section on nitrogen chemistry today. So it says here, the carbonyl carbon is electrophilic, right? Whenever you guys see a carbonyl, okay, I hope you just think, well, there's my carbonyl, and I know it's got a strong dipole going this way, right, which renders the carbon delta positive. So that means a carbonyl carbon is an electrophile. And not only can you see that with the induction, what I just drew, but you can also see that when you draw the resonance forms, right? This is going to be the dominant resonance form, but in this resonance form, there's nothing wrong with this. You can see a positive charge right on the carbon. And so is the carbonyl carbon electrophilic? Oh, you bet your Bobby socks it is. Okay, it's very electrophilic. So that's something that we're going to see time and time again, is that nucleophiles are going to react with a carbonyl, which is electrophilic. So a little bit more on that, okay? If we think about the carbonyl carbon, okay, if I just redraw a carbonyl carbon like this, we all know that the carbonyl carbon is sp2 hybridized, and therefore it is trigonal planar, right? It's flat. The bond angle is 120 degrees here. So what that means is that the nucleophile can attack from either face of our carbonyl. It's not really going to discriminate because it's flat anyway. But when the nucleophile attacks, you can see that what we produce is something that's tetrahedral. So we not only change the hybridization of the carbon as it goes from sp2 to sp3, but we also change its molecular geometry as it goes from trigonal planar to tetrahedral. So that's going to be another huge component of what we see when we look at these nucleophilic addition reactions. So when it comes to the reactivity of aldehydes and ketones as electrophiles, you might be wondering which one is more susceptible to nucleophilic attack. Well, it turns out that aldehydes, generally speaking, are going to be more reactive towards nucleophiles than a ketone is. Now, why is that? It's a twofold reason. Number one is sterics, right? If you think about a ketone has two R groups, right? So it's going to be more encumbered than an aldehyde, which only has one R group, and the other group is a hydrogen. And a hydrogen is the smallest atom in the entire periodic table. So that's one reason. The other reason is an electronic effect, believe it or not. But if you remember, R groups are electron donating via, they donate electron density. And so if you look at the induction between the R groups, right, and the carbonyl carbon, well, the R groups do donate some electron density, which makes the delta plus a little bit smaller. Whereas in an aldehyde, you only have the one dipole. So there's only one electron donating group that stabilizes that positive charge. And so aldehydes, not only are they less sterically hindered, they're more delta positive. So it's a double whammy. So aldehydes, again, generally more reactive towards a nucleophile than a ketone. Now, it turns out that some nucleophiles require acidic conditions, while other ones require basic conditions. So if we think about the Grignard reaction, this was covered way, way back in chapter 12. So Grignard is back in chapter 12, if you want to go back there. That actually worked in basic conditions, right? We could not even have water present. So in the first step, you can have no acid or H2O present. Why? Because the Grignard reagent would just rip the proton off of your water or your acid and destroy it. So in the first step, if you have your methyl Grignard, that's going to do a nucleophilic attack like this, and then you end up doing the proton transfer with water or aqueous acid. Either one is totally fine. And then you protonate to get your alcohol. So generally, a strong nucleophile, like a Grignard, means the reaction is under basic conditions, okay? Generally speaking. So there's nothing really new here. Again, this is something that we covered in detail way back in chapter 12. So under basic conditions, however, can you have a nucleophile react with a carbonyl under basic conditions? Sure. It reacts under the same generic mechanism, okay? Your nucleophile attacks your carbonyl. You break the pi bond between the carbon and the oxygen. Then you form something that is tetrahedral. So you start with an sp2 hybridized carbon. Then you have an sp3 hybridized carbon. Then you do a proton transfer and you end up with your alcohol. So it says here that the nucleophile attacks forming a negatively charged intermediate. And that is this guy right here. And then it gets protonated in the second step upon acidic workup. Now here it says water. In this step, you could write H3O plus. Either one is totally acceptable. There's not one that's right and one that's wrong. They're both completely fine. It would actually kind of depend on the situation. So if we're in acidic conditions, however, okay, in that case, you're not just going to, if you're in acidic conditions, you're not just going to have some nucleophile come in and attack. That doesn't happen. Because under acidic conditions, you're not going to have anything with a negative charge. You're not going to have anything strong enough to react with your carbonyl. And so when we're using a weaker nucleophile under acidic conditions, okay, what's the first step? The first step is actually a proton transfer to make what we call an oxonium ion. So this is called an oxonium ion. And this is a good electrophile. And then this, when you make the oxonium, this is a very strong electrophile. So this is a much stronger electrophile. So now it's going to be susceptible to nucleophilic attack. And notice that after the nucleophile attacks, you don't end up with a negatively charged intermediate overall. So there you go. So when you have the oxonium ion, it can be attacked. So the oxonium ion can be attacked by a weak nucleophile because it's such a powerful electrophile. So again, acidic conditions are required to get a nucleophile to attack your carbonyl when your nucleophile is weak. Okay, a weak nucleophile is not just going to go ahead and react with a carbonyl. It's got to be protonated first because, again, like I said, this is a good electrophile. There's nothing wrong with it, electrophile. But after you protonate it, then it becomes a very powerful electrophile. I mean, super reactive. You see the positive charge right on the carbon in this resonance structure right here. So what's our conclusion? Try to remember this as we go through these concepts today. The protonation of the carbonyl makes it a more powerful or a better electrophile. Okay, so getting into some minutia here. This is kind of just like a interesting way of starting the concepts here. But see if you can follow along with me. And then on the next slide, we're going to get into a whole bunch of different nucleophiles that we could react with. But check this out. It says, when your nucleophile attacks the carbonyl group, the equilibrium depends on the ability of the nucleophile to function as a leaving group. Now, we know that chloride is an excellent leaving group. It says here, good. I'd say even better than that. So in this case, the chloride can leave, no problem, okay? So that's not an issue whatsoever. So it turns out that in this case, you actually get it's mostly the ketone at equilibrium, okay? You have very little of the product in here. So more correctly, the arrows would be drawn like this, okay? It's mostly the ketone. Again, chloride is a really good leaving group. There's no newsflash there, okay? Chloride is the conjugate base of HCl, which is a strong acid. So what we're going to do in this chapter is we're going to uncover a real holy host of nucleophiles, okay? So we're going to talk about oxygen as a nucleophile, whether it's with water, okay, or an alcohol, or a diol, okay? Either way, we're going to look at water as a nucleophile. We'll look at H2S as a nucleophile, or a dithiol, right? Remember, SH is a thiol, so a dithiol. We'll look at nitrogen nucleophiles, whether it's a primary amine or a secondary amine. We'll look at hydrogen nucleophiles. If you're looking at these and going, well, I already know LAH and I know sodium borohydride, you're right, you do, but we're going to revisit them a little bit. If you're looking at this and saying, I thought I knew the Grignard already, you do. We're going to, again, revisit it a tiny bit. Cyanide is a nucleophile. We'll talk about that. And then we're going to talk about this reaction here, which is one of the most important reactions that you'll ever cover. It's like up there with Grignard, is a Wittig reaction. Okay, so we're going to talk about the Wittig reaction. And Wittig won a Nobel Prize for his reaction in 1979. So, you know, if you want to find a way to or if you want to win a Nobel Prize as an organic chemist, what do you have to do? Find a new way to make carbon-carbon bonds. All right. So now that we've got that, let's strap our skates on. And let's turn our attention to oxygen nucleophiles. And I don't want to go too far with it because there's quite a bit of content in it. Well, let's give it a shot. Let's see where it takes us. So, ready? Here we go. Now we're going to kind of go through these, okay? So kind of the rest of the chapter is going to be walking through oxygen, then sulfur, then nitrogen, then hydrogen, and then the carbon nucleophiles. So we're going to start back here. Okay, we're going to start with oxygen nucleophiles, and this will be covered in section 19.5. And the reason I said strap your skates on is because in this section, let me just go ahead and I'll show you something that's really important in here. It's this mechanism here for the formation of an acetal. Okay, and we haven't gotten there yet, but we're going to in a few minutes. This is not a mechanism that traditionally I don't ask my students to draw this entire mechanism from soup to nuts. Maybe I have and I don't remember, but it is one of the most important mechanisms that you'll learn in this chapter. And it is tested, okay? If you look at ACS, they test this. If you look at MCAT, they test it. All those exams test this mechanism. And so if you think, oh, I'll just memorize it, I would say that's really difficult. It's better if you can draw it, right? Write it down, and that way, you know, you start kind of understand the rationale as to how the formation of an acetal works. So I want to try to get here with you in just a few minutes, but let's go back to the beginning, okay, with oxygen behaving as a nucleophile. So let's start at the top. It says, in the presence of water, okay, in the presence of water, a ketone or an aldehyde is actually in equilibrium with a hydrate. So this is actually a new functional group. A hydrate is a functional group. And I need you to know that functional group, just like you know alcohol, okay? Just like you know ketone, aldehyde. You need to know the hydrate functional group. So a hydrate is when you have a carbon that's got two hydroxyl groups on it, okay? We call that a hydrate. So you can see here, this is acetone, and this is just the hydrate of acetone. And it says here that equilibrium, generally speaking, does not favor the formation of the hydrate, except for very simple aldehydes. An example would be formaldehyde. Formaldehyde actually mostly exists as the hydrate in water. But again, you don't need to have that memorized or anything. You need to know that when you take a ketone or an aldehyde, put it in water, you end up with some of the hydrate, okay? Now, it turns out that this reaction is really slow. If you just take some acetone and mix it with water, the reaction is very slow and you only form very little of the hydrate. However, if you add some acid or some base to the condition, so one or the other, not a combination, but one or the other, the reaction rate increases quite a bit. So check this out. Under basic conditions, it wouldn't be an acid that's your nucleophile, it would be hydroxide, right? Let's say you have, something like sodium hydroxide, okay? If you're in sodium hydroxide, right, hydroxide will be your nucleophile. So what does that mean? It means the first step is going to be a nucleophilic attack, okay? Because hydroxide is a strong nucleophile, So it's just going to attack the carbonyl, which is a good electrophile. You end up with this tetrahedral intermediate here, and then the proton transfer is going to be the next step, right? Because your sodium hydroxide is dissolved in water, right? Sodium hydroxide is aqueous. So you have water kicking around, and you do a proton transfer, and you're done. Okay, so you end up with your hydrate. Okay, so that's base catalyzed. However, under acidic conditions, right, if you're in acidic conditions, that means you've got a mixture of H3O plus and water. Okay, so what's going to happen is the water is not a strong enough nucleophile to just go in and attack it. That can't happen. Okay, so what's going to be the first step? The first step is going to be protonation of the carbonyl oxygen by acid to give you an oxonium ion, right? You form the oxonium, this guy here, and now this is a very, what did we call it? A very powerful electrophile. Again, can't see anything. Excuse me, electrophile. Okay, so now that that's protonated, now water can come in and act as a nucleophile. So we form another oxonium ion, and then we have water that can behave as a base in this case, right? And so we end up deprotonating the oxonium ion, and we end up with our hydrate. Hydrate like that. Sorry, I just unplugged my iPad by accident. All right, here we go. All right, so our hydrate. So this is a real David Klein thing, okay? I remember learning this, and nobody preached this to me, but it's very much a textbook thing. This is particular to our textbook. Is he always hammers this to his students. He says, keep this in mind. If you're drawing a mechanism in acidic conditions, okay, if you're in acidic conditions, you cannot draw strong bases. Just don't do it because they can't exist, okay? However, if you're in basic conditions for your reaction, you cannot draw any strong acid in there, right? It won't exist, okay? I don't know if people find this helpful or not. I mean, it's something I guess I kind of figured out as a student, but yeah, hopefully you'll find this useful. So when you're practicing drawing your mechanisms, if you're in acid, don't draw any bases that are strong. And if you're in base, don't draw any acids that are strong because something would be really wrong in that case. So let's take a look. What if we changed, instead of talking about water as your nucleophile, what if we changed it to an alcohol, right? What if we swapped the water out for an alcohol? Then what's going to happen, right? In the first step, you can see that we're in acid here. Remember that when you see the square brackets here, this means catalyst, okay, a catalytic amount of acid. So the first step is going to be protonation to form the oxonium, like this, right? That's your first step. So now one of the molecules of the alcohol can come in as a nucleophile. I'm kind of getting mechanism happy here. But the bottom line is now you make a new functional group where instead of a hydrogen here, you have an R group. So we don't call this a hydrate. This is called an acetal. And this is a new functional group that you have to know. So it's like a carbon with two ethers attached to it in a way. This is called an acetal. It's a very important functional group. It's going to come up like Avogadro's number of times in this chapter. So we form an acetal and we lose water. We lose water in the process, okay? So if you're wondering, what is this acid catalyst? It just says H+. Well, there's two types or a couple types of acids that we use for catalysts. I'd say one would be paratoluene sulfonic acid. We call this TSOH, or sometimes we call it PTSA for para-toluene sulfonic acid. Either one is fine. And then, of course, you all know sulfuric acid off by heart, right? What do those have in common? They're both very strong acids. But the bottom line is that you don't need a lot of it. You just need one drop, and it catalyzes the reaction over and over and over. So what's the bottom line? Is that you have a ketone or aldehyde. It reacts with 2 molecules of an alcohol to give you an acetal plus some water. So let's take a look at the mechanism. And again, I put a red star on this because you have to know this mechanism. You might not be asked to draw it from soup to nuts, but standardized exams like ACS, DAT, MCAT, they like to ask questions about steps of this to make sure that you understand what's a proper intermediate and what's an improper intermediate. Okay. Now, to break it down, the way that the textbook breaks it down is he said there's kind of like 3 steps before you form what's called a hemiacetal. So a hemiacetal is when we have an R group and another R group. We have it's like you have an ether and an alcohol on the same carbon. This is called a hemiacetal. Okay. So not only do you have to know the acetal, you have to know the hemiacetal. So the first 3 steps get you to the hemiacetal, and then the last 4 steps take you to the acetal. And in the last 4 steps, that's where you lose the water. Okay. Hopefully that'll help. You're going to have to look at it a couple times, but let's take a look at the entire mechanism. So remember, overall, what we're doing here, okay, if I can just write it down quickly, is that you have your carbonyl, you have 2 equivalents of your alcohol. Darn it, I meant to put 2. So 2 equivalents. Come on. 2 equivalents of your alcohol. You end up forming an acetal. Okay. Plus you lose water. Okay. You might recognize this because it's this reaction right here. Okay. It's just the mechanism of that reaction is all we're looking at. Okay. The mechanism for this reaction. So remember, is an alcohol a strong nucleophile? No, it's a weak nucleophile. Okay. If you don't remember that, okay, that was covered in chapter 7 of Organic Chemistry 1. So the first step is the protonation of the carbonyl with your acid catalyst to make an oxonium ion, right? That's this guy right here. Now it's susceptible to nucleophilic attack by the alcohol. So it attacks, we go from sp2 to sp3 hybridization. Now you have a new oxonium ion, so the conjugate base of your acid catalyst comes in, it removes this proton, and you've got your hemiacetal. So you're basically almost at the halfway point. Now remember, you're trying to get 2 OR groups, so you've got to lose this, and this gets lost in the form of water. But remember, hydroxide can't just take off here. You can't do that because you can't have hydroxide in strongly acidic conditions. So what does that mean? You have to protonate it first to convert it into a good leaving group, which is water. So the water leaves, but it can't just leave and form a carbocation, right? It's going to get stabilized by this lone pair on the oxygen to give you this oxonium ion. Now, a second molecule, or the second molecule, second alcohol is going to come in. You get a nucleophilic attack. Then all you have to do is do one more proton transfer, and it takes you over to the acetal like that. Okay? Now, that's me talking through it. You can't learn it by listening to me talk through it. Okay? You've got to practice it. Okay? You have to practice this in order to master the formation of an acetal. But the idea is, if you looked at every single one of these steps, what do you notice about all the arrows, all the reaction? They're all, did anybody notice this? They're all in equilibrium. Everything's in equilibrium. And if you're looking at that going, well, if all 7 steps are in equilibrium, what's the chance of it getting to the end? Okay. Well, how would it get there? Well, the answer is, since the acetal is not favored at equilibrium, it's only favored with really simple aldehydes. What you can do is you can take advantage of Le Chatelier's principle, and you can distill the water out of the reaction mixture. So if you convert this to a gas and it evaporates, it's going to push the reaction forward. So that's how you do it, okay, is you just evaporate the water. You use a special distillation technique. It's called a Dean-Stark trap. You don't need to know, about it, but that's how you remove the water. And then based off of the Chatelier's principle, it pushes the reaction forward. Okay, so if you're still, on the fence with me, okay, if you're like, what are we talking about exactly? We're talking about is this. Let's review it one more time, okay? If you take a ketone or aldehyde, that's my eraser, you combine it with an alcohol, 2 equivalents of it, right? 1 mole of this with 2 moles of this, and an acid catalyst. An acid catalyst. You form an acetal, okay? Then we said, what are the possible acid catalysts? We said you could use PTSA or sulfuric acid. They're both very strong acids. So then we said, let's take a look at the mechanism. So this is the mechanism of that reaction. And we said, well, how do you get it to go to completion? The way you get it to go to completion is you remove the water, okay? If you remove the water, which I told you can be done by distillation, it pushes the reaction in the forward direction based off of Le Chatelier's principle. Now, if you're saying, okay, that's great, but what the heck is an acetal used for, okay? You've never brought them up before, why today, okay? Well, the reason why is because if you remember protecting groups, right? If you remember the silyl ether, we took the alcohol and we protected it with the silyl ether earlier on. An acetal can be used as a protecting group. And one of the most commonly used acetals for a protecting group is a cyclic acetal. So we take this compound, which is ethylene glycol, which is the major component of antifreeze. And if you do your acetal formation, so the first 3 steps, you get your hemiacetal. The last 4 steps, you get an acetal. But now your 2 R groups are tied together, right? So you get a cyclic hemiacetal, or sorry, a cyclic acetal. The cyclic acetal, excuse me, is oftentimes used as a protecting group. Now, with a protecting group, you have to be able to remove it. So how do we do that? Well, the good news is when we want to make our acetal, what do we need? We need 1, 2 equivalents of our alcohol. We need a catalytic amount of acid, and we have to remove water. So remember, it's the removal of water that pushes the reaction forward. And so to remove the acetal, to go back to the carbonyl, all you do is put a catalytic amount of acid and just dump it in water. Okay? And that's going to remove the acetal completely. So this mechanism is just the reverse of this mechanism. That's all it is. So again, the reason why we would want to make this is that this is a good protecting group. You see it right here. Acetals can be used as a protecting group. So if you're like, are we expanding our number of protecting groups? Yes. So we started out with the silyl ether that we talked about in chapter 12 when we discussed Grignard reactions. And now we're going to look at a protecting group for a ketone or an aldehyde. Now remember, the reason we learned acetal formation at the beginning of this chapter is because acetal formation only works with aldehydes and ketones. It doesn't work with esters and carboxylic acid. So that's going to be useful if you want to do a reaction like this one. Here we have a ketone, and here we have an ester. Now, what if I wanted to reduce only the ester? Now, remember, we talked about the reduction of an ester with lithium aluminum hydride. We talked about that way back in chapter 12. It's a good reaction, but the problem with that is if I just took this compound and treated it with LAH, followed by aqueous workup, what I'm going to get would be this. I'd reduce this to an alcohol, and I'd reduce this to an alcohol. So what if I don't want to reduce that? What do I do? Well, the answer is I protect the ketone as an acetal. Then I can selectively reduce the ester with lithium aluminum hydride. Then I can remove the acetal with dilute sulfuric acid. So let's take a look. So the first step is going to be using ethylene glycol, a catalytic amount of acid. We always put minus H2O. That's just to let everybody know that we're doing it in anhydrous conditions. We remove water by distillation. It pushes the reaction forward. And now we have our acetal and we have our ester. Because remember, this only works on an aldehyde or a ketone. So now in the next step, we can use lithium aluminum hydride to reduce the ester to the alcohol. And remember, the second step after lithium aluminum hydride reduction was treatment with H3O plus. But this H3O plus does two things. It not only is the workup for the lithium aluminum hydride reduction, but it also removes the acetal. Removes acetal. So if you're like, it's a kind of a 2-for-1, yep, it is a 2-for-1, which is a good thing, right? Has good atom economy, good for the environment. We're all winners, right? Anyhow, so there you go. Now the hemiacetal, a little bit about the hemiacetal. I want to share a couple of things about hemiacetals before we take a break. A hemiacetal, we saw, was formed along the way, right? We said there was 3 steps, then you form the hemiacetal, then 4 more steps, then you form the acetal. It turns out that hemiacetals are actually pretty difficult to collect and just isolate. However, a cyclic hemiacetal is very common, okay, and is usually, or can usually be isolated. In fact, you see them all the time in your everyday life. If you've ever studied the chemistry of glucose, if you look carefully at the structure of glucose, check this out. If you look at this carbon, see it goes oxygen, then another carbon. And then if you look at this, it goes carbon, oxygen, hydrogen. So this carbon, this is actually a hemiacetal on that carbon. That carbon is called the anomeric carbon. It's neither here nor there for today, but the bottom line is that when glucose is cyclized, it actually is a cyclic hemiacetal. So if you remember going back to, what chapter would it have been? I guess chapter 4 in Organic Chemistry 1, when we talked about cycloalkanes like cyclopentane and cyclohexane. You should remember that 5-membered rings and 6-membered rings are highly favored in organic chemistry. So if you can make a cyclic hemiacetal and it's a 6-membered ring, it's going to be favored at equilibrium. Okay, there's nothing wrong with that. But if it's not that kind of ring, if it's just something like this, that's linear, okay, right here we just have 1, 2, 3 carbons in our chain. That's actually very difficult to collect. Okay, very difficult. But again, I want you to be aware of cyclic hemiacetals are a part of carbohydrate chemistry. And towards the very end of this class, I think it's the second to last chapter we cover. It's chapter 24. So chapter 24, we will cover this in some more detail in that chapter. So if you're like, I need to know, well, it's coming up in a few weeks, okay? So what we're going to do now is, I got some questions here. I've got a mechanism question here. I've got a couple of synthesis questions before we get into the nitrogen nucleophile. So I want to take a break. And this is a pretty involved mechanism, this one here, but it is something that we've seen. Okay, we have a strong acid catalyst, so we're going to protonate here to make the oxonium. And I'm going to walk through this with you in a few minutes, but I would like you to take a look at it and try it yourself. And then I don't think there's anything straightforward in organic chemistry, but I think that these questions are doable. Right here we have a terminal alkyne, which you need to deprotonate and then add ethyl iodide to it. But you have to have the carbonyl protected, because when you treat that with your strong base, the strong base could act as a nucleophile and attack that carbonyl. And so it's the same rationale here. You want to protect this as a cyclic acetal. So we'll take a short break. We'll give these the old college try. And then after that, we'll get into nitrogen nucleophiles. And I'll talk to you about some new functional groups like the imine and the enamine. The imine is named after, I thought I had it in here, so maybe I don't, because imines are actually named after a guy. His last name is Schiff. Sometimes they call them the Schiff base. Anyhow, there we go. So we're going to take a break, and then we're going to come back and try 19.8A and 19.10A and B. All righty.